Right. So this is something this paper is something, the work for it is something I've been working on for the past few years. And it kicked off really during COVID when I had a chance to work from home and think about things I'd worked on for 30 or 40 years and never really had the chance to write up. So this is a product from that terrible period. Um, the title, as Richard said, was a model for the crustal structure of southern Britain. And I'd just like to acknowledge my colleagues, David Beamish, John Williams, John Carney and Phil Wilby, who made major contributions to the paper that was published in the Journal of the Geological Society in December 2023. No. Good. Right. We're moving. So I'm taking for granted that you know a little bit about Caledonian geology, and you know that Lake District here in northern England was located on a Caledonian terrain called Avalonia, um, uh, which includes Britain, Ireland, parts of southern Ireland, and the maritime provinces of Canada, and a few bits of the of USA as well, like Maine and so on. This was a terrain that split off from a much larger continent called Gondwana. Now, I think most people will be familiar with the Gondwana concept. Yeah, the geology which you're familiar with in the Lake District here was formed about 450 million years ago and was superimposed on an older basement which was derived earlier on, perhaps 100 or 200 million years earlier, on the fringes of Gondwana. And Gondwana, as you can see here in this reconstruction, includes South America, Africa. It's a slightly strange perspective on the continents, so you may have trouble recognizing. I think Saudi Arabia is in here as well. So and then Australia is out of sight. India is out of sight around the around the pole here. So anyway, there was this large towards the end of Proterozoic time, about 700 million years ago. There was this large supercontinent called Gondwana, composed of these what are now a number of separate continents. I was going to say that the nature of the exposure of these Ediacaran rocks, these rocks that are about 565 million years old, is very different to the Lake District. In the Lake District, you've had tertiary uplift, and apart from the complication of glaciation, which serves to obscure the outcrops, most of the geology is easy to look at and in 3 dimensions. In Charnwood, things are much more difficult because the Charnwood is a massif, but it's a massif that was submerged in Triassic times. So this is Barden Hill Quarry with its very spectacular so-called wadi of Triassic sediments blanketing out the Precambrian rocks. And as you can see, the Precambrian has a lot of relief on it, and these would have been like Inselbergs in the Triassic landscape. So the big problem is that although our largest outcrop of Precambrian rocks in southern Britain is at Charnwood Forest, actually, it's the actual outcrop of the Precambrian rocks is much more restricted because of this blanketing of Triassic rocks. Anyway, the Precambrian rocks that I want to talk about here are these dacitic and andesitic porphyries, which are intrusive domes into volcaniclastic sediments. And these are a bit like some of the things that you see in the Lake District much later, about 200 million years later. There are some fine grain rocks as well. This is a very distinctive volcanic rock called a dust tuff with fine lamination. This is like a tephra, a fine volcanic material, mostly glass and ash falling into a shallow submarine basin. And Getting back to that unconformity again, you can see that in many of the cleavage surfaces here, there is this manganese coating, and that's telling us that the Triassic unconformity was just a very short distance above these things. They were probably stripped off during the Ice Age, the remainder of the Triassic here, but so the unconformity is close by. These are the bomb rocks. This is like an agglomerate screen of dacite and andesite blocks, marginal to one of those intrusive domes. There are debris flows as well, which form very useful marker horizons. You can see that the bedded volcaniclastic rocks are all sort of slumpy around. This is not tectonic folding. This is actually syndepositional contemporaneous folding, contemporaneous with volcanism and development of paleoslopes. So this stuff sort of slumping off. These form useful mapping horizons as marker zones. And finally, from the outcrop pictures, is my colleague John Carney, who is one of the authors of the paper. He's on a field trip last summer, and he's demonstrating the memorial slabs, which are the ones that contain little impressions of of examples of the Ediacaran biota. John's showing a picture there of some of these things, the best examples of these things. But Charnia is one of these things. You're all probably familiar with Charnia, but they're now recognized, well, many species in Britain, and they're comparable to things that are found in Newfoundland, Mistaken Point, in China, in Siberia, and so on. This is this so-called Ediacaran biota. And one of these things, and I think John has got a picture of it here, one of these organisms has been definitely identified as a coral-like animal now, a sort of a real stem coral. So some of these things are definitely regarded as animals now. So these rocks are very important. They record a very important event in the history of the development of life. So that's why we're really interested in studying them. Now, in 1987, we published this early model for the terrains of southern Britain, and they included this blue one, the Charnwood Terrane, and this orange one, this Wrekin Terrane. And these were recognized on the basis of the very different geochemistries of the volcanic rocks that were found in the Charnwood Terrane and the Wrekin Terrane. The Charnwood Terrane was recognized to have sort of rather primitive basaltic lavas, the sort that you get in volcanic island arcs. And the Wrekin Terrane, named after the Wrekin mountain up here in the Uriconian sequence, was found to have much more calc-alkaline sort of basalts. And separating them was this fundamental tectonic line called the Malvern line, which is a major lineament with an important outcrop of plutonic rocks, dated at about 680 million years. That's the Malvernian. But the important thing to note is just how tiny these outcrops of Precambrian rocks are. So here's Charnwood Forest, here's Nuneaton, there's the Malverns, and there's the Wrekin. Of course, the Uriconian rocks have a larger outcrop because they also include the Longmindian complex. So that's a bigger patch too. But the important thing is all these outcrops are very restricted and they are tectonically controlled. So we're getting a rather strange sort of sample of the crust. But on the basis of this very distinct chemistry, chemical variation, I propose that these terrains have been brought together by accretionary tectonics. And part of the thinking at the time was that we knew that Anglesey was in tectonic contact with North Wales along this Slene shear zone, a ductile shear zone, and all the evidence seemed to point that it was of Precambrian age. So accretionary tectonics was in, and that sort of was the general picture throughout the Avalonian terrain, for example, in North America as well, in Canada. One other tectonic boundary which I should mention is this important here, the Friscan Front in southern Britain. This is the thrust edge of the Variscan belt that continues over from Europe, and it's basically a thin skin detachment which becomes deeper uh, as you go south. So this is like a nap complex which is covering the southern edge and apparently truncating this Precambrian material here within what we call the Midlands microcraton. Okay, well, the 1987 model had a few problems which became apparent very rapidly, really. Um, for a start, there's this problem about the concept of an Avalonian origin. People talk about the Avalonian orogeny, but there's really no such thing. And strong fabrics and metamorphism associated with compression or deformation are absent after about 600 million years. The basically the volcanic rocks and volcaniclastic sediments are beautifully preserved, have well preserved textures, and there may be a bit of cleavage, but there is no high grade metamorphism like there is in the Malverns at 680 million years. Older ages greater than 620 are restricted to west of the Malvern lineament, and studies of the magnetic anomalies in the crust uh, by myself, Mick Lee, and Jack Soper revealed that the pattern, the crustal structure of southern Britain was actually much more complicated than just a pile of volcaniclastic sediments. Then in the early 90s, we found this province of rocks which were giving 620 through to 600 million year ages. And I can just jump back. That's these yellow rocks here, the so-called Fenland terrane. So the boreholes here give 620 through to 600 million year ages. They're in contrast to the Charnian, which typically gives ages of about 565. So this was a bit of a problem. Where did these rocks come here? And how was it that they were so similar to Arvonian rocks over here in North Wales? Very similar in their chemistry, isotope composition, and their textures. There were a lot of felsic ash flow tuffs. So that was an enigma. This is a more general map of the whole Atlantic region with the Atlantic disappeared and a reconstruction showing that we're talking about this massif here in southern Britain, but the same sort of rocks occur over here in Newfoundland, Nova Scotia, New Brunswick, possibly as far down as Florida. That's the light green ones. The dark green ones are the equivalent Variscan massifs like Iberia and Armorica and so on. So as I said, the outcrops are very limited and tectonically controlled. So we seek evidence from other sources, and it can be provided from geophysics, as I shall come to. But an important source of information is from the deep boreholes that are in this area. So we drilled a borehole for geothermal research at Morley Quarry in North Charnwood. Another borehole was drilled by the Land Survey people in about the 1960s at Withycombe Farm near Banbury on a magnetic anomaly, and it discovered some very interesting rocks which are key to our hypothesis. Further west at Kempsey and Netherton, there are some more boreholes, and Shell drilled another one up here at Heath Farm, and these provide evidence for what is happening in the marginal area of the Charnian terrane. So this basically is our revised model for where we think the different rock types are distributed, and the blue area is basically what we now refer to as the Charnian domain rather than the terrane, because it seems to be injected into older rocks, including well, the oldest ones are over here. They're presumed to be the same as the Malvern plutonic rocks, perhaps 680, with some younger rifts, and then these Fenland rocks at about 620. But the Charnian terrane the Charnian domain is apparently in an extensional relationship with regard to these older rocks, because there's no sign of or little sign of tectonic deformation in them. So these are the borehole logs. So we've done a survey. We've checked the physical properties of these sequences. So Kempsey and Netherton boreholes go down 500 meters or so below the floor of the Permo-Triassic in the Worcester Basin, and the logs, of course, are much more muted than you get from more recent sedimentary rocks, but we can still see finding upward cycles that I relate to mass flow deposits. They're clearer in this one here. Very clear finding up signatures associated with debris flow units that are associated with subaerial eruptions flowing into shallow marine sediments. And the one at Morley Quarry is clearer because we're actually able to do a detailed log through the whole sequence and identify these debris flow units that are similar to the ones I showed you in the outcrop. When we looked at the petrophysics, key things are to look at the densities, which are very high, up to 2.81 at Withycombe Farm, for example, and the sonic velocities. Where's the sonic? They are typically coming up towards 5 kilometers or even 7 kilometers a second. So these are quite. So this is convincing evidence that these rocks are Precambrian, although we haven't actually dated them, not all of them. When we look at the geochemistry, this is a very commonly used plot for the geochemistry. It's the so-called Pearson-Kann plot. Basically, it's a triangular diagram with titanium, zirconium, and yttrium in the corners, and you grind up your basalts, and you can only apply this to basalts. It shouldn't be applied to more evolved rocks. And there are basically 4 fields in this diagram: a field of island arc tholiites, a sort of a general arc field, a field of calc-alkaline arc rocks, and a field of within plate basalts. And although this diagram has its problems, it's still a very useful way of doing a sort of a quick look at the geochemical variation. And when we apply that technique to the Charnian rocks, these are the Charnian diorites. Many of them are falling in sort of a primitive island arc type field, or just coming across into the mid-ocean ridge basalt field. When we go to Withycombe Farm, same sort of distribution in this primitive island arc mid-ocean ridge basalt field here, same as in Charnwood. When we go to the Morvens, the rocks are becoming more within plate-like and associated with extensional volcanism. And when we go across in further west of the Morvens, for example, look at the Uriconian, the rocks are much more like calc-alkaline arc basalts. So quite a diversity of volcanic types through the area. Now, these diagrams are even more complicated, and I apologize for these. I'll try and explain them briefly for people who are not familiar with geochemical data. These are diagrams that we very commonly use in geochemistry. They're called spidergrams because they look like arachnids. And basically what you do is you'll take your geochemical analysis, you normalize the values, the contents, against a content known from a mid-ocean ridge basalt standard. So basically it means that it's a log scale. So over here, for example, it means that the content of potassium is 10 times greater than that of a mid-ocean ridge basalt. And of thorium, it's almost 100 times greater. So that's the thing. The point is that, again, these patterns show that there's variation, the same sort of variation from that triangular diagram. This chemical variation from place to place within southern Britain in the Precambrian rocks. And interestingly, as the sequences become more evolved, as we go towards from a basaltic composition to a more felsic composition with fractionation, what we observe is that elements like titanium and phosphorus become increasingly fractionated, and that's because these sequences are being affected by fractionation of minerals like magnetite containing titanium, apatite containing phosphorus, and also zirconium as well. So this is an interesting feature, and it's typical of many volcanic arcs, and it certainly seems to have been an effect in our Charnian situation. So the real breakthrough was to get involved with Dave Beamish and his modeling of aeromagnetic anomalies. And basically, the aerom I'm talking about is dominated by one very large aeromagnetic anomaly here. Over the years, it's been studied by various geophysicists who've all come up with various explanations from it in various ages, from Precambrian right through to as young as Carboniferous. And there was pretty little agreement about what the cause of this anomaly was. There's a magnetic anomaly associated with the Morvans over here, and then up here there are some associated with Ordovician magmatic rocks, same age as those in the Lake District. So it's this anomaly here that we modelled. It's called schema. It's called the South Central England magnetic anomaly, and it's a very strong feature. There are hints of it continuing south of the Variscan front, but as you can see, the Variscan front seems to cut it off, and it's obscured down here in the south. So the inversion modelling, this is a bit technical, and I shan't labour too much with this, but just to point out that the modelling was based on the aeromagnetic data set that was acquired from 1957. So it's a really old vintage data set, but it's been polished up by using this new modeling technique. And basically, we've created a three-dimensional model which has dimensions of 225 kilometers by 275 kilometers by 34 kilometers deep, which is the depth of the crust, or roughly we think. And that generates a magnetic susceptibility prediction through 2 million data points that predict what the magnetic susceptibility that is required at any particular level in that model to generate the observed magnetic anomaly at the surface. So it uses an algorithm that was published in 1996. And well, I won't bore you with these constraints. But just suffice to say that my colleague John Williams built these susceptibility data into a Petrel model, which is a petrophysical model, which will be familiar to those of you who've worked in the hydrocarbon industry. And it means that you can produce a model that can be sliced tomographically in any direction, horizontal planes or vertical sections. So let's just have a look quickly at the sort of thing we can do with this. Here we've got a horizontal plane through the crust at a depth of 10 kilometers. And you can see our Central England magnetic anomaly very dominant here, with little bits and pieces in the Morvans, in the Welsh borders, and some associated with relatively shallow level Caledonian intrusions, Ordovician age, over here towards the Wash. The magnetic anomaly, the Central England magnetic intensifies as we go down. Here we're at 20 kilometers, sorry, 15 kilometers. Here we've gone to 20 kilometers. Again, it's changing its morphology. What we are seeing is that the anomaly is apparently becoming stronger south of the Variscan front. And also there are these strange loop-like patterns within it. And then possibly a sort of hints of a central rift zone as well. So all sorts of interesting features are coming out that we had no idea existed. We can produce vertical sections for it. This is the north-south section from the surface down to 32 kilometers beneath the surface. So we can image the variable intensity of elements within the magnetic anomalies. This one is the one that's the Central England magnetic anomaly. And there are bits and pieces up here that are associated with Ordovician rocks. But they're much shallower in the crust. It's only this one we associate with the Precambrian rocks that goes right to the base of the crust. Another way of looking at it those were horizontal slices at a constant level. Another way to look at it is to look at the a structural model at various intensities. So this is an intensity model, and you can see that the purple colors here show the intensity at 30 kilometers, and shallowing up through green and red colors to the shallowest levels. And the dominant feature to note is that this prong here away from the main anomaly is at a shallower depth in the north. You'll have unfortunately, yeah. So these are another way of looking at the same data set, the same magnetic model, but just treating it as a structural model with variable depth rather than a horizontal slice. But notice how strong the anomaly appears to become crossing the Variscan front. It's clear that this the anomaly north of the Variscan front is linked to the anomalies south of it as well. And we can visualize this in various ways. Again, this is depth, so purple is deep and orange is shallow. So here's a perspective from the northeast. Here's a perspective from the west, showing the deep anomalies under the Variscan belt shallowing as you go up into the Midlands. So we ended up with this sort of model, structural model, whereby the Charnian domain is seen to be as a composite feature. It comprises a central arc core, as proven by the Withycombe Farm borehole, a deep borehole. And it contains all sorts of interesting things like possible offsets, lineaments, possible caldera structures, these circular features that we saw, those annular structures, and also sort of offsets down in the Variscan domain. And also another important conclusion is that what we've been interpreting as the edge of the Midlands microcraton for the last 30 or so years is probably mismapped, and that a boundary with this sort of orientation is probably more appropriate. So if we've got an arc here, then the forearc region is likely to be over here, and the Charnian rocks are obviously likely to be occupying a forearc marginal basin, marginal to this arc. We revised this, commented on this revised boundary here. And the boundaries of the Avalonian terrain itself are likely to be down here rather than at the Variscan front. And this is, of course, concealed by a pile of Variscan naps. So basically the story is that the arc continues beneath the Variscan belt and continues way to the south, probably down as far as the Isle of Wight, where another Variscan terrain is probably involved. And finally, in the Worcester Basin, the rocks are occupying the back arc region to this same arc. And over in west of the Malvern lineament, down here, the rifts like the Uriconian rocks and the Long Mindian, they're occupying ensialic rifts and have a calc-alkaline composition. So one way of visualizing this is my so-called tilted anvil analog, where we can imagine this block of magnetic, more magnetic cumulate rocks underneath the volcanic arc in central England, with this prong pointing northwards in the Midlands. So I find this a very interesting sort of metaphor for the structural strength of this Charnian domain underpinning the Midlands block. And it's a good, of course, it doesn't, when I say this is a metaphor for it, this is not a precise analog. This is, of course, solid iron, and we're only talking about perhaps 2% of titanomagnetite in the crystal cumulates that underlie the volcanic rocks. So obviously a much smaller quantity of iron, but nevertheless it's enough to give those very prominent magnetic anomalies. And a very quick model here. This is something put together by Dave. We'll just show this. We'll spin this round, and maybe you can get some. Here we're looking northwards. Here's this anvil-like block, and here's the prong pointing northwards into the Midlands, and the whole thing is penetrating northwards into the crust of southern Britain. Okay, enough of that. So when I was looking around for analogues for this situation, I was surprised to find one in New Zealand. So here's the other bit of the talk where I'll try and convince you that 565 million years ago, uh, southern Britain looked just like Northern Ireland of New Zealand does today. You know that North Island of New Zealand is part of the Pacific Ring of Fire, where crust of the Pacific Ocean is being subducted around these ring of subduction zones and producing very violent volcanism in volcanic arcs. And it looks a bit like this in a section, courtesy of the GNS Science in New Zealand, basically the New Zealand Geological Survey. The crust of the Pacific is being subducted westwards beneath North Island. And as the volatiles come off that plate, fluids rise into the mantle wedge and give rise to partial melting and produce these volcanic rocks of the Taupo Zone, in which some of you may know have visited. If you visited New Zealand, you'll have been to the Taupo Zone and seen volcanoes like Tongariro and so on in your travels. If we look at a map, basically the Taupo Zone that I was talking about there is like a magmatic wedge intruding in from an oceanic marginal basin associated with the Kermadec arc. And basically that marginal basin, an extensional basin, extends in the oceanic crust way to the north of New Zealand, but it's sort of penetrating into New Zealand in North Island. Then the whole system is brought to an end here. The subduction zone, the Hikurangi subduction zone, is terminating here, and then displacement is taken up on the Alpine Fault, running down into South Island. We've got volcanic rocks in the Taupo Zone, including we've got some quite primitive ones in along the island arc tholiites along the Kermadec Ridge. But behind that, there is another rift zone with the so-called Taranaki volcanics. You may know it more familiar as Mount Egmont. There's another rift zone with a more calc-alkaline, more enriched magmatic signature further back. The purple lines here represent the contours of the subduction zone. So here it's at the ocean trench level, of course. And then we go deeper here, 100 kilometers, 150, 200. So the subduction zone is deepening in this direction. And these are some of the volcanoes. We've got White Island here, which is down here. It's just across the ocean continent boundary. And you'll recall that there was a catastrophic eruption there in 2019 and killed quite a few people, tourists visiting it. And then the very elegant cone of Tongariro and behind it Ruapehu, they're further south in the Taupo Zone. They are part of this penetrating magmatic wedge, penetrating from the ocean crust into the continental crust, the juvenile continental crust of Northern Ireland, of North Island. Because just as in southern Britain, the continental crust here is quite juvenile. It's only a few 100 million years older than the ongoing volcanism. So we can make a comparison. We can flip New Zealand around a vertical axis, spin it round, and we can make the comparison of this penetrating magmatic wedge in the Taupo Zone, comparable to the Charnian complex here. And we could speculate that the the back arc rifts, like the Taranaki volcanics, were in a sort of similar position to the rifts like the Uriconian Longmindian complex, and also various bits and pieces in South Wales in the back arc region of our English situation, sorry, English and Welsh situation. Now, not far to go now, but the situation is actually more complicated, even so, because paleomagnetic evidence suggests that um, southern Britain, was actually rotated 180 degrees round from its current position, its current coordinates, and it must have, if that's true, then Britain must have rotated probably at the end of Cambrian times through about 180 degrees during those Caledonian plate movements that I was talking about earlier on. So this is the reconstruction I favour, with Britain pointing here towards the Gondwana margin, and basically the what we've been talking about is the Charnian domain forming a rift penetrating into the Gondwana margin, propagated in from oceanic crust of Iapetus, the developing Iapetus Ocean further north. Britain at that time would have been at a high southern latitude, probably about 50 degrees south. And it's got a long way to go, of course, northwards before it ends up in the position we're at today. So these are my conclusions, and I've got a, a little synoptic video which I'll show you, but we'll end recording after I've made my conclusions. So a new model invokes emplacement of an enzymatic rift wedge, the so-called Charnwood domain, into the northern accretionary margin of the Gondwana supercontinent, which we now call the Marches terrane. So that terrain was just a region of Gondwana that subsequently split off to form Avalonia. And the Charnwood domain is just an extensional domain within it. A high-resolution inversion of the aeromagnetic data set provides new insights into the structure of this cratonic area, and deposition of the Ediacaran strata with their important biota occurred in an arc basin, a four-arc marginal basin, marginal to the Charnian arc. Significant geochemical and structural variation observed in a small region of crust is replicated in a modern analogue in North Island, New Zealand. And I should have said that those maps I presented comparing North Island, New Zealand with southern Britain, they're the same scale. So just to give you a feel for the scale of the processes. And this model, I believe, explains much better the unusual geophysical properties and mechanical behaviour of the crust of the Midlands microcraton in the early Paleozoic, its successor, the Anglo-Brabant Massif, in the late Paleozoic time, and finally, what is referred to as the London platform in Mesozoic to Cenozoic time. But basically, these are all in the same place. They're just different manifestations of this crust that was created in latest Precambrian time.